Hi. So this particular video is going to be just an introduction to the ideal gas law. There'll be another one that follows it. All right. So we probably have been exposed to the ideal gas law in the past, at least if we're looking at this as physics students. We probably had chemistry in the past at some point where we would have seen this before. So I'm keeping that in mind as kind of like a starting point for anybody watching this. So this is going to be a reminder of what the ideal gas law is. So if we've got a container filled with some gas, then the pressure inside that container, the volume of the container, and the temperature of the gas inside that container, as well as the amount of gas inside that container, are all interrelated with this ideal gas law. The ideal gas law says that the pressure of the gas times the volume of the gas is equal to the amount of the gas times this constant R times the temperature of the gas in Kelvin. So this is an important note here that when we're using this ideal gas law, that we have to have temperature in Kelvin, and we should have pressure in pascals, and we should have our volume in cubic meters. So the amount of the gas that we have, we're going to measure that, at least for this particular equation, in terms of the amount of moles of gas present. And we'll jump into what a mole is here in just a moment. But what this means is that what this equation means is that if I've got this this gas there, and maybe it's a fixed volume, maybe something like I've got a gas in my coffee mug here, and I say throw a flame underneath it. I'm going to be increasing the temperature of the gas inside of this coffee mug. So as a result, what would happen? The pressure of the gas inside that coffee mug would increase. Okay. Raise the temperature, you're going to raise the pressure. Let's see, if I lower the temperature, I'm going to lower the pressure. We could have something like a balloon filled with gas. And let's see what happens when we put that balloon maybe in liquid nitrogen. Liquid nitrogen is going to cool that balloon down, and it's going to cause the temperature to drop. That's going to cause the volume of the balloon to decrease as well. So all of these are kind of interrelated with the ideal gas law that we see there. Now, in terms of number of moles, how do we measure that? Well, at least for this class, the only thing we're going to worry about is the definition that you see there on the bottom of the screen there, the equation you see on the bottom of the screen. This says that the number of moles of molecules of the gas is equal to, well, the number of total molecules of the gas divided by Avogadro's number. And Avogadro's number is 6.022 times 10 to the 23rd. Now, I don't want you to be freaked out by this. A lot of people have a lot of issues with the concept of moles, probably mainly because of the fact that the number is something we can't really get a good grasp on. This is the same concept as using something like the term dozen to define how many of some objects is present. So for instance, if I had, say, I don't know, 36 eggs, then I might say, well, instead of calling it 36 eggs, I might say it's 3 dozen eggs. Okay, well, what have I done there? I've taken the number 36 and divided it by the number in a dozen. That's 12. And now I know that I've got 3 dozen eggs. Okay, same thing here with the number of molecules. I take my number of molecules and divide it by, let's see, the number of molecules present in a mole. Number of items present in a dozen is 12. The number of items present in a mole is 6.022 times 10 to the 23rd. So I just divide that total in by 6.022 times 10 to the 23rd, and that will give me the number of moles of gas that I've got present. Okay. All right, we can take this ideal gas law, this PV is equal to nRT, and we can substitute in that expression for number of moles. And when we do that, we can develop a whole nother equation for the ideal gas law. It's right here at the bottom of the screen. So let me just highlight that real quick. There's another equation for our ideal gas law. Not only can we have PV is equal to small n times R times T, we could also have PV is equal to NKT. K is just another constant. That's Boltzmann's constant. That's 1.38 times 10 to the negative 23rd joules per Kelvin. And that capital N there, what is that? That is the number of molecules. Okay, so we have two different forms there of the ideal gas law. We can use whichever one we want, whichever one is convenient for the problem that we happen to be working on. All right, so a quick conceptual question here. We've got a can of compressed air or a fire extinguisher. Why does it get cold when we spray it? Well, take a look at the ideal gas law. We've got some amount of gas trapped inside of that fire extinguisher. When we spray it out, what happens? Well, N decreases. Okay, yeah, we're causing some of the gas to leave. What else happens? Well, the amount of pressure is going to decrease as well. And what happens as a result, more due to this, the pressure decreasing, then, the number of moles of gas or the amount of gas changes. But in addition to the amount of gas changing, the temperature also drops. Okay. So the pressure goes down and the temperature goes down as well. And also, the amount of gas drops too. Okay. So by spraying out some of the contents, the pressure drops inside the container and the temperature is going to drop. And this is probably something that we've experienced. All right, so let's see about this problem here. So we're thinking about the interior of our lungs. Inside of our lungs are these little tiny air sacs called alveoli. And we're given the average radius of these alveoli. There it says it's 0.125 millimeters. And it says that the air that they contain inside them is composed of 14% of it is oxygen. Our goal for this particular problem is to figure out the number of oxygen molecules present in one of those sacs. Okay, so that's our goal. We're given a couple things. We're given the pressure. So the pressure is 1 times 10 to the 5th pascals. And we're also given the temperature, and that temperature of 37 degrees Celsius, that's body temperature. Of course, you remember that we cannot operate in Celsius. We have to operate in Kelvin. We add 273 to 37 to get our temperature in Kelvin. Our temperature in Kelvin is 310 Kelvin. While we're at it, the radius of the alveoli, that's given in millimeters, but really we probably should have that in meters instead. So let's make a conversion there. We divide by 1,000. That number is a bit unwieldy. Let's put that in scientific notation. There we go. Okay. All right. So looking through at what I've got here, I've got the temperature, I've got the pressure. Let's see. And I've got PV equals what? NKT is probably the form that I want to use. So let's check off what we have. We've got the pressure. We've got the temperature. That K is just a constant. That's our constant from the previous slide. 2 slides ago, I guess. We want the number of molecules. We're still left with a little bit of a quandary because we don't exactly know what the volume is. Well, these sacs, we can model them as if they are spheres. The volume of a sphere is 4/3 pi r cubed. All right. So given that formula for volume, we can take our value for r and plug it in and get the volume of one of these sacs. Right. Let's put all this together. we rearrange our ideal gas law equation there and solve for, isolate capital N on one side. We get capital N is equal to PV over KT. We can then plug in all of our values, keeping in mind that our volume V is 4/3 pi r cubed. All right. So we've plugged in all our values. And as a result of plugging all this in, we get the total number of molecules of air present. It's 1.9 times 10 to the 14th molecules. Now, only 14% of those molecules is oxygen molecules. So we have to take that number, 1.9 times 10 to the 14th, and multiply it by 0.14 to get the total number of O2 molecules present. All right. So one more, and then we'll take a little break. It says, this particular problem says, we want to estimate the amount of space a mole of air occupies in this room. I guess by this room, I mean my office. Okay, so let's do that. PV, oops, PV, not P. Let's start over. Got ahead of myself. PV equals nRT. We want the number of moles, or we want the amount of space for 1 mole. So we should use this form of the ideal gas law equation. So in this case, N is equal to 1, just 1 mole. Temperature inside this room. In general, 20 degrees Celsius is probably a pretty good estimate for room temperature. That's about 68 degrees Fahrenheit or so. So if I convert this over to Kelvin, it's 293. Oops. 293 Kelvin. Okay, 293 Kelvin. So let's see. I've got the number of moles. I've got the temperature. I know R is a constant. That's 8.314 joules per mole dot Kelvin. I guess the other thing I need is the pressure in the air. The pressure of the air in this room. Now I can pull up the physics toolbox suite app on my phone to get the pressure. And I've done that in the past, and we are going to use an estimate of 96,000 pascals for the pressure in this room. So that pressure is specific to kind of this area of Radford. So where I happen to be, you might say, well, why am I not using sea level pressure? And you could use the atmospheric pressure. The standard pressure that you see in textbooks is 1.013 times 10 to the 5th pascals. You can do that, but I'm just making it a little bit more specific to where I actually am. The pressure here is about 96,000 pascals. All right, so let's get let's solve for volume here. Volume is equal to nRT over P. So our volume then is 1 times this ideal gas law constant, 8.314 joules per mole dot Kelvin, times our temperature of 293 Kelvin, 293 Kelvin, divided by 96,000 pascals. We'll see what that gives us here. If I were thinking ahead, I would have had this done already, but I guess you get what you pay for, huh? There we go. Let's get rid of that streak on this streak this time around. 2.53 times 10 to the negative 5 cubic meters. 10 to the negative 5, no, 10 to the negative 2 cubic meters. There we go, 10 to the negative 2 cubic meters. Okay, 2.53 times 10 to the negative 2 cubic meters. Well, that's great. What does that mean exactly? So let's see, because I don't have a good feeling for how much space that is. That's equivalent to a box, basically a cube that's about a foot by a foot by a foot. And so that's about how much space a mole of air takes up, given a temperature of 293 Kelvin and a pressure of 96,000 pascals. All right, that does it for this one.